Welcome back to the deep dive. If you've ever looked at a really complex data problem and just wondered, how do the pros turn millions of rows into a tool that can actually make a decision? Well, you're in the right place.
Absolutely.
Today, our mission is to give you the complete practical blueprint for building a machine learning classifier.
And the goal here is that you walk away not just knowing the jargon, but really understanding why each step is so essential.
Yeah, the why is everything.
We're taking a deep dive into that foundational workflow, and we're focusing on the steps and, the concepts that are common to pretty much every ML project. It's all built around the Python library, Scikit-learn.
Which is the industry standard, right?
It really is. It's user-friendly, it's reliable, and it's just perfectly structured to help us pull real predictive knowledge out of raw data.
And to keep us grounded, we'll be using the ultimate ML training dataset, the famous iris flowers.
A classic for a reason.
It's just perfect because it lets us visualize the entire classification problem. We're trying to identify one of three species of iris, that's setosa, versicolor, or virginica, just based on two features, petal length and petal width.
It's a beautifully clean backdrop for learning this whole 7-step journey.
Okay, so let's unpack that. The entire ML development process, from that raw data to a deployed model, it's a very structured journey.
It has to be.
The source material we're looking at maps out 7 distinct steps, and I think recognizing this structure is like the first key to mastering the field.
That structure prevents what we call analysis paralysis. It takes something that can feel like this overwhelming creative thing and makes it a manageable, repeatable process.
Right. So here's the roadmap we're following today. Step 1, load the data. Easy enough with tools like scikit-learn.datasets.loaderies.
Yep.
Step 2, analyze the data. Step 3, visualize it. 4, split the data into training and testing sets.
A crucial step.
Then 5, train and test a handful of different models. Step 6, select the best one. And finally, Step 7, deploy the model.
And we really cannot stress enough how important those first 3 steps are. It's all about understanding your ingredients before you start cooking. Exactly. Before you write a single line of training code, you have to know what you're working with. So using a pandas data frame, for example, we check the dataset's dimensions, how many samples, how many features.
You peek at the first few rows just to make sure it all loaded correctly.
Oh, absolutely. Yeah. That initial peek is where you catch those small but fatal errors, like data that looks like text when it should be a number.
Been there.
We also run a statistical summary to see the mean, standard deviation, min-max for every feature. And this whole phase really ends with examining the distribution of your target variable, our iris species.
So what's the breakdown? Are all 3 species represented equally?
Yes. And that breakdown is so important because if your classes are severely imbalanced, let's say 90% setosa and only 5% of the others, your whole evaluation strategy has to change. We'll get to that later.
But before that, we hit step 3, visualization. Why is seeing the data so powerful, especially with an example like iris?
Because visualization is instant confirmation. With the iris data, if you plot petal length versus petal width, you immediately see that the setosa species, it just clusters cleanly in one corner.
It's easy to separate.
So easy. But the versicolor and virginica, they often overlap a bit, and that creates the real classification challenge right there in the middle. Seeing that helps us predict why certain algorithms might struggle later.
So we use what are called univariate plots to understand each feature by itself, and then multivariate plots, like that scatter plot you mentioned, to see the relationships between the attributes. You're looking for those natural boundaries.
Exactly.
Okay, so once we understand the data, we hit step 4. And this is where we start preparing for the actual learning part, splitting the data. Why is setting aside a test set like the single most important decision for practical model reliability?
Well, it's really the difference between memorizing and understanding. If you train a model on all of your data, it'll perform perfectly on that data. Of course it will. Yeah. It's essentially just memorized every single answer.
It's seen the final exam questions ahead of time.
Precisely. But the whole point of ML is generalization. We want it to perform well on new, unseen data. The test set simulates the real world. It's the final exam the model hasn't studied for. If it fails there, it fails in deployment, period.
So what's the consensus? How much data do we set aside for this final exam?
The standard rules of thumb are, 80% for training and 20% for testing, or maybe 75-25.
And when would you choose one over the other?
If your data set is small, you'd lean toward 80-20 to give your model more examples to learn from. If you have a massive data set, you can go 70-30, even 60-40 sometimes.
Got it.
But Regardless of the ratio, there are two implementation details that are just absolutely critical for any professional ML pipeline.
Okay, what are they?
First, use a random seed. This just ensures that when you or a teammate runs the split function again tomorrow, you get the exact same random subsets. It's all about reproducibility.
Makes sense.
Second, and this connects right back to our earlier point about balanced data, you must use stratification.
Stratification. Okay, let's make sure that concept lands clearly.
Think of it this way. If your original data set has, say, 33% of each iris species, stratification makes sure that your training set and your test set also have 33% of each species.
Ah, so you're preserving the original ratio.
Exactly. Without it, a random split could accidentally say, load up your test set with only 2 of the species. That would mean your model would never even be tested on the third class, giving you a completely unreliable result.
That's a great way to put it. You're guaranteeing the final exam truly reflects the course material.
You are.
Now, after splitting, we often run into another critical step, feature scaling. Why do we go through the trouble of applying a standard scaler?
We have to put every feature on a mathematically level playing field. Imagine we were classifying a house, and our features were its square footage, a big number, like 2,000, and the number of bedrooms, a small number, maybe 4. If we feed those raw numbers into an algorithm like the perceptron, that 2,000 square feet will just dominate the calculation purely because it has a much larger magnitude.
So the algorithm would effectively ignore the number of bedrooms.
It would just get drowned out. So
Yeah.
scaling neutralizes that inherent numerical bias. The standard scaler works by estimating the sample mean and standard deviation, but, and this is vital, it estimates them only from the training data,
Not the test data.
never the test data. Then we apply the formula. We subtract that mean and divide by the standard deviation. This basically turns every feature value into a measure of its distance from the mean. Now, a change in square footage and a change in bedrooms carry equal weight.
Perfect. So with our data prepped, we get to the heart of it, the algorithms. Before we jump into model selection, let's start where this whole journey began, the perceptron.
The history here is, it's just fascinating. The idea really started back in 1943 with the McCulloch-Pitts neuron concept.
Wow, that early.
Yeah. They were designing AI by mimicking the nervous system. They imagined this simplified brain cell that acts like a logic gate. It receives inputs, integrates them, and then fires a binary output if a certain threshold is crossed.
So it's literally biology meeting computation.
It is, and it's wild that the architecture we use today, input features multiplied by learned weights, is fundamentally based on that same biological analogy.
That's incredible.
Then, in 1957, Frank Rosenblatt formalized it with the perceptron learning rule. This rule was a way for the system to automatically adjust those weight coefficients based on whether it got a classification right or wrong. It allowed the model to learn the optimal dividing line.
And since we have 3 iris classes, how does a modern perceptron handle that? If its origins are purely binary, fire or don't fire.
Great question. It uses a method called one versus rest, or OVR. So for our 3 classes, 0, 1, and 2, it doesn't train one single algorithm.
It trains 3.
It trains 3 separate binary classifiers. Classifier 1 learns to separate class 0 from classes 1 and 2 combined. Classifier 2 separates class 1 from 0 and 2, and so on.
Ah, so when a new flower comes in, they all vote.
Exactly. All 3 classifiers vote, and the one with the highest confidence wins.
That makes the leap from historical binary logic to modern multi-class classification much clearer. So now that we have that context, let's talk strategy. If we have to train a handful of models, how do we pick them? The source material brings up the no free lunch theorem.
Right. This theorem is sort of the guiding philosophy of model selection. David Wolpert proved that there's no single universal algorithm that works best on all possible data sets.
So you can't just throw XGBoost at every problem and call it a day.
You can't. It means a data scientist should never just assume that algorithm X is going to be the winner. Practically speaking, you have to compare performance. A good starting handful usually includes a simple linear model like the perceptron, a simple nonlinear model like a decision tree, and then 1 or 2 powerful ensemble methods.
Start simple. Establish a baseline, then move to complexity.
That's the plan.
Okay, let's look at that complexity. Starting with tree-based methods, the decision tree is probably the easiest model for a human to understand.
Oh, for sure. It's the ultimate flowchart. It just systematically splits the data with questions like, is the petal length greater than 1.9 centimeters?
And it chooses those questions based on statistical criteria, like Gini or entropy, to find the split that best separates the classes.
Exactly. It's highly visual, very easy to explain.
But those single trees can be a bit unstable, right? change a few data points, and the whole tree structure can shift.
They can be very fragile. And that brings us to the ensemble approach, the random forest.
So how does that tackle the instability?
Random forest doesn't rely on just one of those fragile trees. It fits hundreds of them.
Hundreds.
Hundreds. On different random subsets of both the data and the features. So when it's time to predict, all those hundreds of individual trees vote, and the majority decision becomes the final, much more robust answer. It's the wisdom of the crowd, but for classification.
And then we get to the heavy hitter for structured data, the one that often dominates competitions. XGBoost.
Yeah, extreme gradient boosting.
How is that different from random forest?
XGBoost is a different kind of ensemble. It's sequential, not parallel like random forest. The genius of the gradient boosting framework is that it builds trees one after the other.
Okay.
And crucially, each new tree isn't trained on the original data. It's trained specifically to fix the prediction errors or residuals that were made by the tree that came immediately before it.
So it's sequential error correction.
Oh,
Each new tree is held accountable for the mistakes of the past.
that's a perfect way to put it. The process starts with a really simple initial prediction. Then we calculate the residuals. How far off were we? Then we fit a brand new decision tree, but we train it to predict those errors, not the original iris species.
And then you just add that correction to the overall prediction.
You do, but you scale it by a small learning rate to prevent overcorrection. And you just repeat this hundreds of times, constantly driving those residual errors down towards zero.
It's the ultimate iterative process. And what makes XGBoost so fast and flexible? Why the extreme?
The engineers behind it added some major optimizations. It uses advanced regularization to prevent overfitting, something called shrinkage, which is the learning rate, and clever techniques for handling missing values automatically. But crucially, it's designed to run efficiently on parallel hardware. That's really where the extreme comes from. It's optimized for speed and scale.
Okay, so we've trained our handful of models, Perceptron, Random Forest, XGBoost. Now we have to answer the biggest question. Which one wins? We have to dive into evaluation metrics. What does success even look like here?
Well, we have to start with the simplest measure, which is accuracy, or ACC.
Right.
This is usually the first metric we look at, especially when our data set is well-balanced like the iris data is. It's just the percentage of samples the model got right.
You just count at the ones that got right, the true positives and true negatives, and divide by the total.
Exactly. And the opposite, of course, is the error, or ERR, which is the percentage it got wrong.
But, as we talked about earlier, if our classes are unbalanced, accuracy can be a liar.
It can be a huge liar. If 99% of your samples are Class A, a model that just predicts Class A every single time will have 99% accuracy.
But it's completely useless.
Utterly useless for finding that rare 1% of Class B. So to evaluate performance in the real world, we need to understand the building blocks of error, the confusion matrix.
Okay, let's define those 4 key components again. We have our successes. True positives.
TPs.
Those are the positive cases we correctly identified as positive.
And true negatives, TNs.
The negative cases we correctly identified as negative. Simple enough.
But then we have to analyze the mistakes.
Because the nature of the mistake matters a lot. First, you have false positives, FPs. This is a false alarm. The model classifies a negative sample incorrectly as positive. That's a type I error.
And the other side of that coin is a false negative, FN.
Which is a missed opportunity. That's classifying a positive sample incorrectly as negative. A type 2 error. And this is where we move beyond simple accuracy, because sometimes one type of error is way more costly than the other.
Think about a spam filter versus a medical diagnostic tool.
That's a great application. So in which case would we want to prioritize catching every single positive case?
That would be the medical diagnosis, where the stakes are life and death. If you're screening for a disease, you want to catch every single person who has it. In that case, you want to maximize recall.
Also called sensitivity.
Right. Recall asks, of all the actual positive cases out there, how many did our model successfully find? You want very few false negatives here, even if it means you get a few more false alarms.
So high recall minimizes the missed positives, the type 2 error. But what about the spam filter?
For a spam filter, you prioritize precision. Precision asks, when the model predicts an email is important, so positive, how often is it actually right? If your filter has low precision, it's flagging important work emails as spam. That's a high number of false positives.
Which is really annoying.
Very annoying.
Yeah.
So to minimize that, you want high precision, even if it means a little more spam gets through to your inbox.
That contrast makes it so clear. High recall minimizes missed opportunities, FNs. High precision minimizes false alarms, FPs.
And if you need a single number that balances both of these competing goals,
You use the F1 score.
you use the F1 score. It's the harmonic mean of precision and recall. And because of how the math works, you get a low F1 score if either your precision or your recall is low. It forces the model to be good at both.
That brings us to the end of our deep dive. We've mapped out the 7 essential steps, traced the history from that first MCP neuron to the perceptrons OVR method, explored ensembles from the simple decision tree to the hyper-optimized XGBoost, and learned how to pick a winner by understanding the trade-offs between accuracy, precision, and recall.
And if you are taking these steps yourself, just remember the selection principle. Initially, we use accuracy on the test split to filter down our models, but the final selection has to involve a deeper look at the business cost of FPs versus FNs. And a crucial tip: always go back and actually look at the misclassified samples, the false positives and false negatives. They often tell you more about the true complexity of your data than any single metric ever can.
So, what does this all mean? We started this journey with a perceptron, which was designed to mimic a biological neuron, a biomimicry approach. Then we saw that the state-of-the-art XGBoost is really just pure optimization. It's a sequential mathematical engine designed to ruthlessly hunt down and correct errors.
Two very different philosophies.
So given that we have models from emulating the brain and models from pure computational efficiency, which approach, biomimicry or optimization, do you think holds the greater promise for breaking through the next major wall in machine learning? That's your thought experiment. Until next time.